Alright guys, it's Professor Floyd again, and we're trucking through this homework 10 number 2. And here we have the classic Dutch boy saves the village by sticking his finger in the hole in the dike. So the idea here is, or the idea behind that lore is that if you allow the water to continue to flow, it will erode the dike. So if you stop it, then wait for the floodwaters to subside, then the dike will hold. So we want to know, is it really possible that a little Dutch boy could have stuck his finger in a hole and applied enough force to be able to keep all that water from coming out? So what we have is a dike with the water, the ground, and then some hole, and maybe the little boy is walking by and he sees, oh no, there's a hole. And so he sticks his finger in that hole. And it turns out that there are 12 feet of head from the water level to where he is sticking his finger in the hole. And we know that the hole is the size that he can stick his finger in it. So we'll say that the whole area of the hole is a half centimeter squared. Alright. So this is really just hydrostatic pressure. So if we look at Bernoulli's equation and we take our formula for hydrostatic pressure, so we've got it right here. Hydrostatic pressure, our delta P is going to be equal to the density of the fluid times the force of gravity times delta Z, the change in height, the head on the head of water. So here the only thing that's sort of complicated is that we have metric and English units mixed up. Oh, sorry. So we want to find out what the force is, and we're asking for it in pounds. So that's really not that big a deal. But we've got to remember that pressure is equal to force divided by area. So if we calculate the hydrostatic pressure, we know how hard the water is pushing out, and then we know the size of the hole that it's pushing out of, and so we know how hard the boy will have to push in to balance the hydrostatic pressure. Sorry. So that's the bigger context. So ultimately our force is going to be equal to the pressure times the area. We know the area, we're going to calculate the pressure so that we can calculate the force that he has to apply. So our pressure is going to be, or our change in pressure, but it's going to be a positive pressure because we're building a head up, is going to be equal to 1,000 kilograms per cubic meter times gravity, which is 9.8 meters per second squared, times our change in height, which is 12 feet, and then 1 meter per 3.28 feet. So delta P equals 1,000 times 9.8 times 12 divided by 3.28. So this should equal to 35,853. We'll call it 854. Not that it really matters. 854 kilograms. And then our feet cancel here. So kilograms, meters per meter, our cubic meters, and seconds squared. So this is pascals. Kilograms per meter per second squared. So we need to get this in English units, so let's just convert from pascals to PSI, and then we can just convert this area into square inches. So pascals times 14.7 PSI divided by 1,01300 pascals. is going to be our measure in PSI. So times 14.7, oops, 14.7 divided by, and so that equals 5.2 PSI. Okay, so we write it as PSI and we kind of think of it's just a unit, it's a single unit. But that's sort of deceptive. PSI is really pounds per inch squared. So you probably do yourself a favor to write it like that. So now we have our force is equal to our pressure, which is 5.2 pounds per inch squared. And then we have 0.5 centimeters squared. And then we know that 1 centimeter or 1 inch is equal to 2.54 centimeters. And so if we just square each of those, now we've gotten rid of our square centimeters and we'll be in square inches. And then our square inches will cancel here. So we do that, we have 5.2 times 0.5 divided by 2.54 squared. And we find that it's 0.403. So 0.4 pounds that the boy had to apply. So I have small children. I have a 7-year-old son and I have a 4-year-old daughter, and I can tell you they can certainly apply 0.4 pounds of force with that little finger of theirs. Jab you. So definitely that little Dutch boy could have saved his village. Now let's say, what if that Dutch boy got kind of impatient and he called and called, nobody would come, nobody would bring a wad of gum, and nobody would bring any clay or anything, a stick. So he had to go to the bathroom or whatever. He got impatient, he got scared, and he ran. So he pulled his finger out of the hole. So what would be the flow rate of the water coming out of that hole, supposing that the hole did not change height? So now this is a special case of Bernoulli's equation called Torricelli's theorem. And Torricelli's theorem basically says that the velocity of the liquid coming out of a hole that's perpendicular to gravity will have the same velocity as if that parcel of water had fallen that same height differential. So the force or the pressure from the hydrostatic pressure is going to accelerate and cause that parcel of water to move as if it had dropped the same vertical distance. And so Torricelli's theorem is simply that the velocity of exit will be equal to the square root of 2 times gravity delta z. That's pretty straightforward. Changing delta z. Yep. Got that up there. So I think we can handle this. The velocity is equal to the square root of 9.8 meters per second, and then second squared. And our change in that was, do I have that written down somewhere? Let's see if I've got it written down, so I don't have to convert it again. 3.66 meters, so 12 feet. And then that 12 feet is 1 meter per 3.28 feet. So this comes out to, should come out to 3.66 meters. So if we look at our units, we have meters squared and seconds squared, but we're going to take a square root of that. So we're going to end up with meters per second, which is velocity. That's what we want. So we can calculate this pretty easily, and we find that 2 times 9.8 times 3.66, and then take the square root, is 8.47 meters per second. But I believe, what did we ask for? Right, we want to know what the flow rate will be. So again, we go back to flow. Q equals velocity times area. So the area is, and we want to know the flow in liters per minute. So our Q is equal to our velocity, which is 8.47 meters per second, and our area was 0.5 centimeters squared. So we've got to get those to square meters. I keep on setting my stuff down. And so centimeters, we have 1 meter, 100 centimeters. Square it, square it. Yep. And so our Q will equal, those go away, and these become cubic meters per second. And we're looking for QLPM, liters per minute, or liters per minute. Okay. And so this comes out to 8.46 times 0.5 times divided by 100 squared. Comes out to 4.23 to the minus 4 cubic meters per second. And then we should know by now that 1,000 liters is equal to 1 cubic meter. And of course, we all should know that 60 seconds is equal to 1 minute. And so our flow in liters per minute is times 1,000 times 60. So it should be 25.4 liters per minute. That's coming out pretty fast from such a small little hole. It's about like that. Okay. All right, guys.